The option of a note card is there for you on your test. Okay. That's the only thing you should have out. Also, if you are a person who struggles with simple multiplication or division, you may have a standard calculator. Standard calculator means non-graphing. So if you want to bring a standard calculator, I have a few. You'll just have to wipe them down when you're done. They're not all guaranteed to work perfectly, but I do have a few if you feel like you need one. But it's just a standard 10-key calculator for you to add, subtract, multiply, divide. Okay. So if you want to bring that on Friday, please feel free to do so. Again, it's a non-graphing scientific calculator. Today, we are verifying inverses algebraically, and we do this by using composition. So the key concept here is composition of inverse functions. Basically saying that if you compose the original function and its inverse together, it should always reduce down, simplify down to just x. Okay, if it does not simplify down to just x, then they are not inverses of each other. So it comes down to us, are you able to combine like terms? Can you distribute? Can you multiply? Things like that. So for example, if you look up here, we have f of x equals 1/4 x plus 3, and g of x equals 4x minus 12, right? So the first thing you're going to do is compose. So you're going to do your fog first. So when I fog, that means I'm taking g of x and I'm plugging into f. So what is g of x? Well, g of x is 4x minus 12. So f of 4x minus 12. Wherever there used to be an x, I'm plugging in all, I'm plugging in 4x minus 12. So I substitute in 4x minus 12. I'm going to distribute. So distribute, distribute. And then I'm going to combine like terms. And notice how it comes down to just equal to x. That's a good sign that these are inverses of each other. Then I go on this side and I check the golf, which is where I'm plugging f of x into g. What is f of x? Well, f of x is 1/4 x plus 3. So I substitute that in. I substitute, I distribute, and I get x plus 12. Combine like terms, and I'm left with just x. Because each composition equals x, the functions f and g are inverse functions. And that's how you algebraically show that two functions are inverses. All right, so we're going to do our little quick review. Verifying graphically. So remember, when you verify graphically, the two functions are supposed to be reflected over the y equals x, and y equals x is just a dashed line through the origin at the points where y and x are the same value. So here's my y equals x line. Okay, so with my y equals x line, and now I'm going to graph 1/4 x plus 3. I start at plus 3, so I'm starting at 0, 3, and my slope is rise 1, run 4. So I go to 0, 3. I'm going to rise 1, run 4. 1, 2, 3, 4. Rise 1, 1, 2, 3, 4. I'm going to reverse it. Down 1, 1, 2, 3, 4. Down 1, 1, 2, 3, 4. So here's my first line that I'm going to do my very best to connect. And then I'm going to check the other one. So this one is 4x minus 12. Well, this is a little harder. Its slope, it's a y-intercept is at negative 12. Sorry, 0, negative 12. Do I have the ability to start at 0, negative 12? Yes, no, maybe so. No, I don't. So I have to find another point to start at. So I can actually find the x-intercept here. Remember, the x-intercept means you plug in 0 for y. So I can't start at my y-intercept, so I'm going to start at my x-intercept. So at my x-intercept, plus 12 plus 12, that gives me 12 equals 4x, divide by 4, and that tells me that my x-intercept is at 3. So I'm starting at 3, 0. So I'm going to start at 3, 0. So 1, 2, 3. And my slope here is 4 over 1. So I'm going to rise 4 and run 1. So rise 4, 1, 2, 3, 4, run 1. Rise 4, 1, 2, 3, 4. 4, run 1. There's that. Opposite. I'm going to go down. 4, 1, 2, 3, 4. And left 1, 1, 2, 3, 4. And right 1. I'm going to do my very, very best. Pretend that I went through that first dot. Then I went through that second dot. And so now I've graphically shown that these are inverses of each other. And I know that they're graphically inverses because one, they intersect on the line of reflection, and they are literally reflected over y equals x line. All right, so are you comfortable seeing it graphically still? Yeah, okay. Or there's more than one way to graph a linear equation. Notice how I could not use my y-intercept, so I had to go find my x-intercept, and then I use my x-intercept along with my slope to graph my line. All right, so we're going to do this together. We're going to prove or disprove that 2x plus 4 and 1/2 x minus 2 are inverses of each other. Okay, so the first thing we're going to do is fog. So that means we're going to substitute g of x in for x in the f function. And what this looks like is that f 1/2 x minus 2. So what that means is wherever x is, which is there, I'm plugging in this guy. So continuing that, it becomes 2 times 1/2 x minus 2. I distribute. A 2 times 1/2 is x. 2 times, I forgot my plus 4. 2 times negative 2 is negative 4 plus 4. When I simplify, negative 4 plus 4 is 0, and I'm left with just f. This is a good sign. So we're taking our composition skills and just using them to verify inverses. Now we're going to do the golf. G composed of f. So now I'm substituting f of x in for x in G. So G 1/2 x minus 2. So where x is, which is here, I'm now plugging in. I put the wrong thing, y'all. Oopsie. You see nothing. I'm now plugging in 2x plus 4. So that equals 1/2 times 2x plus 4 minus 2. So I literally am just substituting it in. I'm going to distribute 1/2 times 2, 1/2 times 4. Half of 2 is 1, half of 4 is 2, minus 2, plus 2, negative 2, cancels out, equals 0, and bam, I get x for both. So that means that f of x and g of x are inverses. So we're taking our composition skills from Monday and we're applying them today. Questions, comments? No. So this is a linear example. We're going to next do a quadratic example. Okay. So the quadratic, we're going to do the same thing. We're going to do the fog first. So that means we're going to substitute g of x in for x. So that gives us f of the square root of x divided by 3. So wherever x is, and f of x is going to become the square root of x divided by 3. So this equals 3 parentheses square root x divided by 3 squared. 3 times, what does squaring a square root do? It gets rid of it, right? It's its inverse, so it goes away. So I'm just left with x divided by 3. 3 times x divided by 3, and that equals what? It just equals x because your 3's equal 1, which can become Casper, the friendly one. And then here we do it again. But this time you're doing golf. So you're substituting in f of x. So you have g composed at 3x squared. So I'm taking this, plugging it in here. So that gives me the square root of 3x squared divided by 3. When I simplify this, my 3's again become Casper the friendly one. And I'm just left with the square root of x squared. The square root of a square is its self. So both sides equal x. That means that f of x and g of x are inverse. All right, you do have classwork through Canvas online, but there are also sometimes people like to practice physically. So if you flip over, there are some practice problems. So in your workbook or on this paper, you can practice verifying. Remember, practice makes perfect. This is strictly practice. It is not a credit. It is not a grade. It's just that if you want to practice the skill of verifying and composing, here are 8 practice problems for you to do so with, okay? So again, these are just practice problems. Got it? Cool. If you go here, so after you do your do now, if you hit next, it takes you to the notes that we just did. It'll take you to the notes we just did. And then you hit next, and it'll take you to your assignment. So your assignment is Salvis Pearson 1-4 verify inverses algebraically. It tells you to upload your work from the workbook to this assignment. It is a Google Classroom assignment, so you'll click on it, go to your classroom. Please make sure you are in the right classroom. Okay. When I export grades, some people's grades didn't go where they needed to go because they were in the wrong classroom. So please make sure you're in the right classroom. And that is it. This completes our unit. We have finished Unit 1.